In this lecture, we're going to provide an introduction to the concept of variability as one of the most important aspects in statistical applications. And so when we talk about variability, we're referring to the extent to which scores differ from each other within a distribution. And there are three aspects and important elements to variability. And the first is that variability provides an indication to how consistent scores are in a distribution. Generally, the greater the variability of those scores, the lower the consistency. The second aspect here is that variability describes the accuracy of the central tendency measures. So the greater the variability, the less accurate the mean will describe the entire sample or the distribution. And it provides, and the third aspect is that provides a very important measure of how spread out a distribution is. And so there are a number of ways to quantify variability. The first and simplest approach is to calculate the range. And the range refers to the distance between the high and the low value, or the maximum and the minimum value. And this basically provides us with how spread out all of the data are. And so this is a crude measure of variability, which is just a mathematical difference between the high and the low value. Now, for nominal and ordinal data, this is the measure of variability that is used. The next measure of variability, which is going to be very important, involves tracking variability with interval and or ratio type of data. And that's something called the variance and the standard deviation. And so this is a numerical value that provides information as to how spread out the scores in a sample are around the average or the mean. And this all begins with calculating something called a simple deviation. And a deviation refers to how far a single value, a single research participant score, is from the average score of that sample. And so we refer typically to the magnitude of a score's deviation as an error. And so if we take a look at the equation below, here we see to calculate a deviation, we take the score obtained from the first research participant, and we subtract the group average. And we keep the order, and understanding that the deviation value can be a positive or a negative value. We don't switch it halfway through. So we will actually end up with 10 deviation scores if we have 10 research participants in our sample. So the number of deviation scores will equal the sample size. Now, because these scores, some of the scores will be positive, some of the scores will be negative. When we add up, so here we see the summation notation symbol once again. When we take the deviation scores of each score and we add them all up, it will equal to 0. And so that tends to provide what's called the zero-sum problem in trying to capture with one value how spread out the scores are in a sample. So one approach here is to calculate something called an average deviation, because each research participant score will deviate by a different amount from the average. We want to get one number that gives us some indication of how much the average each of those deviations are. That gives us that overall picture. So the average deviation here, as you can see, is just simply adding up all of the deviation scores, keeping the order here with the raw score and the average, and then we add it to the next score, subtract the average, the next score, subtract the average, so on and so forth, and we divide it by 10 if there are 10 participants in the study. If there are 20 participants in the study, we would have 20 deviation values we add up and divide it by 20, where n is the total number of participants. The problem here, if we go back to slide 28, if we add up all the deviation scores, and we know that all the deviation scores will sum to 0, then the 0 divided by the sample size is still going to be 0. So we still have our zero-sum problem here when trying to calculate some number that represents how spread out the scores are in a sample. And this is because scores are balanced around the mean. And so we will work an example a little bit later, but this proved to be a big problem in terms of moving forward with the development of statistical testing. And so a number of years ago, within the early part of the 20th century, two scientists, Sir Arthur Eddington and Sir Ronald Fisher, both were statisticians, mathematicians. Sir Arthur Eddington was an astrophysicist, and Sir Ronald Fisher was a biologist. And they both proposed separate approaches in dealing with the zero-sum problem. Sir Arthur Eddington suggested that for each deviation value, the absolute value is calculated, and in doing so, the negative sign is removed. So what will result are all positive values divided by n to get an average deviation score. Sir Ronald Fisher proposed a different approach. He said instead of calculating the absolute average, square the deviation score. The squaring aspect would carry out the same function as the absolute value in getting rid of the negative sign. And so this proved to be a bit of a debate and challenge between these two scientists in terms of how to move forward in accepting which approach is the better approach. So in terms of which deviation measure won the debate, the squared deviation proposed by Sir Ronald Fisher is the one that was eventually used, that led to the development of further statistical tests throughout the 20th century. And mathematicians determined that this was a more efficient, mathematically a more efficient way than using the absolute measure, because in the long term it tends to produce smaller errors under ideal conditions, at least mathematically. And because the squared deviation is used in subsequent calculations, it was found to be much easier to manipulate algebraically than the absolute deviation. And so up to this point, beyond the early part of the 20th century, when various fields, including mathematics and statistics, accepted the squared deviation approach, all inferential statistics beyond that were developed based upon the squared deviation model here. So this ends this introductory lecture in Unit 3 on variability.